Hi guys, this is Dr. Gonzalez here, and in this video I'm going to talk to you about experimental design. I know at the beginning of the course we had a very brief introduction to experimental research. We're going to go a lot more in depth in this one to talk about all the different ways that we can design experiments to achieve our research goals. So we're going to talk about experiments. So experimental design is a research method, and it is specifically aiming to establish cause and effect relationships between two variables. Remember, you have an independent variable and a dependent variable. The independent variable is the one that you, the researcher, are going to manipulate, and you're going to observe its effect directly on the dependent variable or the measured variable. And the goal of any experiment is to establish causality, not an association. If we were going to do a non-experimental measure like a correlation, we could establish causality. But most experiments already have some previous research that's been done for them that has established that relationship between those two variables. So in an experiment, you've got specific components and specific procedures. First of all, an experiment has to have a manipulated independent variable. You, the researcher, are going to change or set levels of your experimental or IV. At the same time, you're going to have controls that are going to be taken care of either through your design or through your sampling or through your statistics. Those are extraneous variables, and we're going to try to minimize their effect because we truly want our cause and effect relationship to be between our independent and dependent variables. And then lastly, we have random assignment. Participants are going to be randomly placed into groups, and that distributes any variability that you might have in your participants across your groups equally. So if one of those three components is missing, your causal conclusion is going to be weaker than it needs to be. Now let's review variables in experiments. We've talked about this a little bit in previous chapters and videos, but we're going to get more in depth here. So an independent variable is your variable that is causing a change in your response variable, and the response is going to be your DV. In an experiment, the IV has to be manipulated. Why? It has to be manipulated because it represents the cause in a cause and effect relationship. I can't have a cause and effect relationship without a cause. And your independent variable has to have two levels or conditions. Now that might be receiving the IV and not receiving it in a simple design, or it may be different levels, say, of a drug or a condition like sleep. The examples I have underneath there are all ways that I could set specific levels in an experiment. I could have some participants sleep for 4 hours, other for 8. I could be exploring different therapy types. I could have some assigned to a group to receive CBT, cognitive behavioral therapy. I could have another group that's not getting any treatment whatsoever. And then maybe I'm looking at how well you perform on a test, depending on your study method. And maybe you're just going to use flashcards for one, and the other you're going to reread your assignment notes. The bottom line is, without manipulation, you don't have an experiment. So in an experiment, an IV has different levels. Levels are going to be specific conditions of the independent variable. So the example I have here for you is, say we're in a study exploring caffeine intake on sleep duration. I have 3 different levels of that independent variable. You can either receive 0 milligrams of caffeine, 100 milligrams of caffeine, or 200 milligrams. So it has 3 different levels there. Your dependent variable is your measured outcome. And we're looking for changes in that DV that are going to be specifically caused by your independent variable. So this is representing your effect. And just as any other variable in your study, it has to be operationally defined and very clearly measurable. So examples might include a test score, % correct, reaction time in milliseconds, or your anxiety level, which might be a scaled score. So if you can't measure it, you can't test it. And we're going to spend time talking about measures in another video. You also have control variables, and these are variables that we're going to hold constant across all your groups in order to prevent alternative explanations from coming in. So imagine that you're doing an experiment about sleep deprivation and reaction time. So my independent variable is sleep deprivation. My dependent variable is reaction time. Control variables would be things that I need to hold constant across all those groups. I need to test both of those groups in the same testing environment, preferably in the same room at the same time of day. I need to use the same reaction test. Those control variables are going to help me isolate my independent variable as the only causal variable in the experiment. Now, control variables are absolutely essential because what they're doing is they're eliminating an alternative explanation. If you have multiple variables changing at the same time, you're not going to be able to determine causation. And if you've successfully controlled all the other variables there and only your independent variable changes, then you've set up a study that will allow you to make a causal claim. Now, extraneous variables are any variables other than that independent variable that might influence your dependent variable. These variables are always present in the real world research. You're going to have to deal with them. They're not necessarily a problem if you control them. And these could include things like participant motivation, prior knowledge, fatigue, or environmental distractions. And let's discuss environmental distractions, right? We want to keep those environmental distractions down. So say you are giving a test and you have one group come in and it's nice and quiet, and then you have another group come in and they are doing yard work outside with a lawnmower and a leaf blower. You've now introduced an environmental distractor into that experiment there. Obviously, it was not intentional, but it could impact your results and lead to a conclusion that's incorrect. Now, you can't and you do not eliminate all extraneous variables. It's impossible to do that. Instead, you're going to control or reduce their influence. Some of the strategies we might use to achieve that would be having identical experimental conditions, like the room we just talked about with the noise. We're going to use standardized instructions. You're going to have your instructions written down, and whoever is directing your group is going to read those instructions and not deviate from one group to another. We also use random assignment to place our participants in their individual groups, and there are some methods of statistical control that we can use as well. Now, a confounding variable is a specific kind of extraneous variable. And if that variable changes along with your independent variable, you've got a dangerous situation. You've now introduced another plausible alternative explanation. So imagine you're testing a new teaching method. You want to see if this new teaching method is effective at getting your students to perform better on a recall memory test. Your experimental group has their new method in the morning. Your control group gets their old method in the afternoon. You've introduced time of day as a confound. Why? Well, students may get tired towards the end of the day, and that could impact your results. So you can't isolate the effects of teaching method, time of day, or both. So what you need to do is test both groups in the morning or both groups in the afternoon. Either way, you would be controlling for that variable. Confounding variables represent a direct threat to causal relationships. When you have a confound, you cannot isolate that independent variable. There are other things out there that could be varying at the same time. They could be impacting your dependent variable, and you simply cannot tell the difference between the impacts of those different variables. That affects the ability to interpret your results clearly. And from the outside, your study may look very well designed and very valid, but because of that confounding variable there, it is fundamentally flawed, and that impacts your ability to determine a causal relationship. So confounds versus extraneous variables. They are not exactly the same. An extraneous variable is an outside influence on the DV that may or may not affect your results. A confounding variable systematically varies along with your independent variable. So it's actively distorting your results. So extraneous represents a possible problem, and a confound is an actual problem that might ruin your conclusion. How do we control for these variables? First of all, we want to hold variables constant. So we want to do things like keeping our conditions exactly the same across all groups. We want to use the same room, the same lighting, the same instructions. We also want to use random assignment, which is a requirement for causal conclusions. Our participants are going to be recruited and then randomly placed into groups. That makes sure that differences or variance is evenly distributed across all of those groups. We might find a situation where matching will work for us, and this is where we line participants up and pair them based on key characteristics. So each group is then going to have equivalent participants. So maybe if we're dealing with those tests, academic explorations with experiments, we might match the participants by GPA and then assign them to groups. We also want to have standardized procedures. We're going to use identical procedures for all groups and all participants. And that helps you, the researcher, actively reduce variability that you could be introducing yourself. Now, which strategy is the one you need to focus on the most? No single method is going to control all variables, and no single method is perfect. But a strong experiment is going to combine random assignment, standardization of procedures and rooms, and controlled environments to allow you more control. The more control you have, the stronger your causal claim can be. Now let's talk about operational definitions. So an operational definition is going to provide a specific way how you intend to measure a variable or manipulate that variable. And it's extremely important because, one, it prevents ambiguity. Ambiguity is questioning about how you're doing something. And the doing something in this concept is measuring. It ensures consistency across conditions and across other replicable situations where you want to do this again. It actually allows for replication. So a weak definition for an experiment would simply say sleep. Am I talking about sleep quality, sleep quantity, chronotype? What am I talking about here? A stronger definition would be total hours slept measured using a sleep tracker the night before testing. So that would be a physiological measure, and it's got an active measurement that I specifically lay out beforehand so I know how I'm measuring it. Subject variables are going to be pre-existing characteristics that you cannot necessarily randomly assign or manipulate. And this could be things like age, gender, or personality traits. So these are variables that you might include in the research design, or you might recognize and adjust for in a statistical analysis. They're not going to truly establish causation like an independent variable would, but they may be of interest depending on what your research needs are. We also have certain variables that can be considered mediators or moderators. So a mediator explains how or why the IV affects the DV. So you have an image here that says sleep increases alertness, which improves test performance. So sleep is mediating alertness, or alertness is mediating sleep, depending on how you look at it. But they're both affecting test performance in some way because they flow from one to another. Contrast that with a moderator. A moderator changes the strength or direction of a relationship. So here's an example. Sleep also affects your stress level. So if you're stressed out and you're sleepy, your performance on that test it may be strengthened. In this way, I mean strengthened as in it's less, right? It moderates it because you've got higher stress down here, and it causes your performance to be less improved because I have this other thing out here that's changing the strength of the relationship. Now, let's talk about types of experiments. And on this page, I started out with a picture of a rat that is in a water maze and a picture of a water maze itself in case you've never seen them. A water maze is something that we use in laboratory experiments, and rats and mice inherently don't like water. So you can drop them in this pool here, and they're going to learn how to get to this escape platform. And over here you see visual cues. So the Morris water maze is often used in visual spatial memory and learning experiments that take place in a laboratory. So that's going to take us to our first type of experimental design, which is a laboratory experiment. These are experiments that take place in a highly controlled, very artificial setting. In this setting, you have maximum control over your variables. With rats and mice, for example, you control what they eat, what time the lights come on, what kind of enrichment activities they have. When you're doing these sorts of experiments with participants, you are in complete control of who you're bringing into your lab. Your procedures in a laboratory experiment are also very standardized and they're very carefully monitored. So an example of a laboratory experiment might be testing the effect of sleep deprivation on mice using a Morris water maze. Advantages of a laboratory experiment: you've got a very high level of control over the variables because you have just that one environment that you're dealing with. And that gives you strong internal validity. It makes it a little bit easier for you to establish that cause and effect relationship because, again, you've got control, which affects your internal validity. And because most laboratory experiments follow extremely step-by-step procedures, it's pretty easy to replicate these experiments. The disadvantages are that any environment that is artificial might reduce realism of your results. So it might be great in a lab, but the results you get might have lower external validity. That means they don't generalize very well. And participants may behave differently in a laboratory. So not necessarily the mice or the rats, but yes, they would because they're not in the wild, but people coming into a lab might meet demand characteristics and perform differently than they would in a different situation. Now, field experiments are experiments that are conducted in a real world or natural setting. You're still manipulating your independent variable, but your participants may not even be aware that they're in a study. This might be a situation with deception. And if you go back and review ethics, there are issues with that we need to make sure we've addressed. So an example of a field experiment might be testing whether people tip more when servers smile at a restaurant. The advantages to field experiments is that they give you higher external validity. You're moving from a lab to a real-world setting. The behavior of your participants is going to be more natural and realistic. You're not creating an artificially controlled setting. And that also helps reduce your demand characteristics. But the disadvantages include things like less control over extraneous variables. There's other things in that restaurant that you might not be able to control that may be affecting tipping behavior. Again, it's going to be difficult to replicate this because there are so many different variables working together. And then you also have the risk of more confounds that you have to worry about. Quasi-experiments are experiments where you manipulate your IV but you don't have random assignment. So quasi means kind of, sort of. So your groups are going to be based on a pre-existing condition. So say I want to compare test scores between two existing characteristics. So I have two teachers, class A and class B. I am testing their test scores, but they already existed as class A and class B beforehand, and I'm not using random assignment. Advantages is that a quasi-experiment is often more practical in a real-world setting. I might not have the ability to do random assignment. It's useful when you can't do that. And it can still suggest causal relationships. But because you have no longer met all of the requirements for a true experiment, you have lower internal validity. Remember, internal validity is, can I establish a cause and effect relationship between these two variables? We also have greater risk of selection bias, and you can't necessarily fully eliminate those alternative explanations. We also have something called between subjects designs. And in a between subjects design, each participant is going to be assigned to only one condition. So you've got two different groups that are going to experience different levels of the IV, or you may have more than two. For example, maybe I'm looking at test performance. I have one group that got 4 hours of sleep and the other group got 8. I let them sleep and then I give them their test. This is between subjects. The advantages of this is that you don't have to deal with order effects like practice and fatigue. Remember, if I give a pretest to a participant, and then I let them go for a week, and I have them come back and do a follow-up after I give them the treatment variable. They may carry over some practice or fatigue from that first experience. Between subjects, designs are simpler to implement because you're dealing with these two groups, and that's just it. And it also helps reduce participant awareness of the conditions. So what that means is each group experiences one aspect of that condition, and that's it. Okay? Disadvantages is you've got to recruit more participants because they're not going through both conditions. You've also got problems that creep up when you've got individual differences between those groups. Your variability can be different just based off probability. And you're going to have less statistical power when you compare this to what we call within subject designs. So what are those? Within subject designs are experiments where the same participants experience all the treatment conditions. And you'll notice in the image here, I have this circular relationship. So I have participants that sleep for 4 hours, they take their test. Then they sleep for 8 hours, then they take the test. So each participant is going to act as their own control. Advantages of this is that it allows you to control for individual differences because you're able to track those differences across treatment conditions. Because you're giving that same participant both levels, it requires fewer participants overall, and that gives you an advantage with greater statistical power. The disadvantages are you may run into a situation where you have order effects, like practice and fatigue. You might have carryover effects between those conditions, and it also requires something called counterbalancing. So that's the end of our research design specific video here. Remember to go check Canvas for your instructions, templates, and videos that are going to be related to this week's assignment. I know during this week's module there are a lot of small videos here covering a lot of different concepts, so make sure you've watched them all. And if you have any questions or concerns, make sure you reach out. Take care.